This is section 6.2, solutions about ordinary points for your differential equations. Here's our definition. Consider a differential equation that's a sub 2 of x times y double prime plus a sub 1 of x times y prime plus a sub 0 of x times y is equal to 0. A point x naught is said to be an ordinary point if the differential of this expression now, the normal, where we have 1 times y double prime, and then we have a new function p of x. Essentially, that's a1 divided by a2. And q of x, that's a naught divided by a2. So this new differential equation, the functions p and q are both analytic at x naught. So that means it's differentiable there. And the main thing that keeps it from being differentiable usually is that it's a discontinuity where it would be a 0 of a2. So that's called an ordinary point, is that if it's differentiable there, there's no denominators and nothing to worry about. And it's nice, continuous, and differentiable. That's what analytic means. If at some point you don't have an ordinary point, it's called a singular point. So a singular point is an example or some work that we're going to do in the next section. For this section, we're going to focus on ordinary points. Okay, so our theorem tells us that if we have an ordinary point of a differential equation, then we can always find two linearly independent solutions in the form of a power series. The power series solutions converges to some at least small interval defined where r is the distance from x naught to the closest singular point. So if you have a singular point where the function might not be defined, then you have some finite value for r. If p is continuous for all real numbers, then r is going to be an infinite radius of convergence. So the solution is said to be a solution about an ordinary point, x naught. Okay? All right, let's take a look at an example. Here's our first example. We have y double prime minus x times y prime plus 2y is equal to 0. So we're going to look at this centered around the origin, centered around 0. And if we take a look at it, our p is negative x and our q is positive 2. And both of those are differentiable around 0, infinitely differentiable, so they're analytic, which means our solution that looks like this, a power series solution, is going to have a radius of convergence that's going to be defined for all real numbers. So we're not going to have any singularities. We're not going to have any singular points. So we're going to assume that r is going to be infinite. Okay, that's a theory behind it. Now let's actually figure out how we're going to solve for this. So we're going to solve for this by taking our differential equation and essentially putting in the values for the series that we got. So we need the first derivative, the second derivative, and the original series. And so if this is a series, the derivative is going to be, remember c is a constant, so it's going to be n cn x to the n minus 1. And remember that n is now not going to start at 0 because it's going to give you a 0 term, so we're going to start n at 1. Likewise, the derivative of the first derivative is the second derivative, n minus 1, cn, n minus 2. And again, when n is equal to 0 or 1, it's going to give me a 0, so I'm going to start my indexing at 2 here for the derivative. So this is your second derivative. It goes in the first slot in your differential equation. We have our first derivative that goes in this slot in our differential equation multiplied by x. And we have the original function that's going to be multiplied by 2. So here is our differential equation now in terms of the series. Okay. So we want to see if we can somehow combine this. But before combining it, let's take a look at what's happening here. Maybe we'll look at it in a bigger font for now. We see that there's an x here that we need to put into this distribute. So x times the series is really just going to change your power. So let's multiply the x into here, and then we have n minus 1 plus 1, so that's just going to be n. So we're going to have x to the n power. Negative sign still out here. This 2, we can think about bringing that 2 in as well. So each of your terms in the series will have a 2 in it. So here is our expression now. There's a minus sign that we can put in here, but let's just leave it out for now. And now let's see if we can take a look at the index for each series and the powers. I want them to match. And so I see that I have x to the n, x to the n, and I don't have x to the n here. So I want this to be an x to the n. So we're going to do an index shift. So the index shift here is what you do is you change your n to, I can change it to k, but I'll keep the, well, we can change it to k. So we'll replace n with k plus 2. So I want this to match up with the same index here as n. So if I add 2 to each of these n's, I would have this. So I have k plus 2 in for n, and this would just be k plus 2, and this thing would simplify to k plus 2 minus 1. So we can simplify that. This is k plus 2, and k plus 2 minus 2 is just going to be k. And at the same time, when I do that, I need to subtract 1 from the index, starting index. So k is going to start from 0 this time. So I did my substitution where n is equal to k plus 2. So these things didn't do any shifts, so for the sake of matching up my indices, I'm just going to call this k. But you don't have to. You can just keep it as n, and everything else will follow the same way. So I have k's now after my index shift. Oops. Let's be careful with that. Okay. So again, simplifying this, this is just going to be k plus 2 minus 1. So it looks like it's going to be k plus 1. And this subscript is k plus 2. Oh, sorry. It should be k plus 1. And the index here should be k plus 2. And then this whole power here should just be k. Alright. So now they all have the same x to the k power. And now I want to combine them, but the indices are still different. So what I need to do is I need to take out the k is equal to 0 for 2 of them. So I want this to start with k is equal to 1 because that's my largest starting point. So if I want this to start with k is equal to 1, then I'm going to have in here the k is equal to 0 term. So I want this thing, this expression here, when k is equal to 0. So when k is equal to 0, I can simplify all this. In here I would just have a 2, and in here I would just have a 1, and then this is going to be c sub 0, or c sub 2, 0 plus 2, and then this is going to be x to the 0 power. So I got rid of the 0th term by pulling it out, and then so my series will start at 1. So that's this series where the first term got taken out, and that's exactly what this is equal to. Alright, the second series does not need to change, but the third series also starts at 0. So now I want this series to start at 1, which means within that series I'm going to have this term where k is equal to 0. And I guess that's all we can do, because we can't really simplify that anymore. I mean, x to the 0 is equal to 1, so we can fix that. We'll do that in the next line over here, where x to the 0 is equal to 1, x to the 0 is equal to 1. And so I'm also going to simplify 2 times 1 is 2. And then I'm also going to take them out of the brackets. So let's take them out of the brackets so we can start combining them. So take them out of the brackets. And then now I'm noticing, I'll do this in the next line, I'm noticing that this is not part of the series, and this is not part of the series. So what I'm going to do is I'm going to take this term and drag it out over here. So now I have this, which is not part of the series, and then these series are right next to each other. So that's going to allow me to work with that series a little bit better. So I want to combine these three series, since they're all they all start with the same index now. They all have the same x power. So what I'm going to do is I'm going to take this series and combine it with the first one. So notice that the series all have an x in it, or x to the k. So we can imagine that we can take the x to the k out. So for this series I have k c sub k with a negative in front. So I actually have a minus k c sub k. Whoops. I meant to take this, copy that, and paste it onto here. So that combines these two series into this. If you look at the terms here with an x sub k, I have k plus 2 plus times k plus 1 times c sub k minus k plus 2 minus this thing. And then I factored out an x to the k. I can actually do that with the last one as well, and so this will just be a plus and then 2c sub k. So I can just tack that on towards the end here, and then that gets rid of that my last series. So take a look at this series, the new series that we have, and all the components that are involved. They all have x to the k that got factored out, and so they just have these terms left. I think we're ready to set this up. Actually, we could take one more step and notice that these two terms have a c sub k in it. So let's put those together. So let's factor out, I'm going to put a plus here, and then a parentheses, and then factor out a c sub k. close parentheses, so that we have a couple of terms factored with c sub k plus 2, and then we just have this one term factored with c sub k. Okay. This is all equal to 0, which means each of these, this is a constant, the constant term. When k is equal to 1, that's the linear term. When k is equal to 2, that's the quadratic term, the x squared term. And this is supposed to be equal to all this stuff. So plus 0 times x plus 0 times x squared, etc. So that we're going to have equations that we're going to set up. All right, so that's our first part. And now our second part is setting them all equal to 0 and then seeing what we're going to get. So we have this term that's not part of a series that's equal to 0, and we basically want to find a relationship between these two things. And so the rule of thumb is to have the larger c sub value equal to the smaller c sub value. So in this case, I want to solve for c sub 2. And then if we do that, we bring this 2c sub 0 to the other side. That would become a negative, and then we divide by 2. So that would cancel the 2. So I just have a negative c sub 0. So that's my first relationship that I find. Next is I want to set each of these coefficients equal to 0. Now remember, the x of the k is just going to be the variables. I don't really care much about that. I just care about these things equaling to 0. So we have for n bigger than or equal to 0, or bigger than or equal to 1, we'll start at 1. That's when the series starts. I guess we should be using k. We have this relationship. This coefficient of x to the k is equal to 0. Now remember, I want to solve for the larger one, so I want c sub k plus 2. So what is that equal to? I bring this over to the other side, so that's going to give me a negative of this thing divided by this expression. So a negative of this thing, let's just fix this up a little bit. A negative multiplied through, that will make this into a positive, and that would make this into a negative. So here we have our relationship for c sub k plus 2. And this is going to work when k is bigger than or equal to 1. So what we can do is we can try to figure out how this is going to look like for each of them. So we'll start off with k equals 1, because that's our starting point. K is equal to 1. So let's take this expression and put k is equal to 1 here. So if k equals 1, we're going to get 1 plus 2 is 3. K equals to 1, that's going to give us a negative 1 here. K equals 1. K equals 1 here will give us a 3. K equals 1 here will give us a 2. And so this is our relationship here. We can write it just a little bit better. I got a minus 1 divided by 3 times 2. I know that that's equal to 6, but we'll hold on to that until we see some sort of pattern. And this is c sub 1. All right. So that's what happens when k is equal to 1. So what happens when k equals 2? Well, let me fix this one up real quick. Alright, when k is equal to 2, we're going to take this expression again and change the k's into 2's. So 2 plus 2 is 4. This is going to be 0. This is going to be 2. K is equal to 2, we get 4. K equals 2, we get 3. I suppose it didn't really matter because this whole thing is going to be equal to 0 anyways. So that's gone. Now let's do k is equal to 3. And again, we're going to take a look at this, put 3 in here. We're going to get 5. 3 in here. 3 minus 2 is 1. This is 3. 3 plus 2 is 5. 3 plus 1 is 4. So we have this expression. But what is C3? C3 was equal to this thing, right? C3 was equal to this, so we'll take this expression with a C1 and replace C3 by it. And I'm just going to put it over here at the end with parentheses so it doesn't look like we're subtracting. So let's see if we can simplify that. Looks like we can say this is a negative 1 on top. So that's equal to negative 1 on top. And then we have 4 times 5, and then 5, 4, 3, 2, and then there's 1. So that looks like it's a 5 factorial. And then this is multiplied times C1. So C5 goes back to C3, which goes back to C1. So everything here can be in terms of C1. We have C4 goes to C2. Well, this one actually, C4 is actually equal to 0, so that's gone. Let's keep going here. We'll give k is equal to 4 a try. And once we start seeing the pattern, then we can kind of see if we can just summarize things. But let's see what we can anticipate. When k is equal to 4, we have C6. K is equal to 4. 4 minus 2 is 2. This is C4. 4 plus 2 is 6. 4 plus 1 is 5. But what's C4 equal to? Well, C4 is equal to 0. So this whole thing must equal to just 0. So we see that C6 is gone. Let's do one more, C7. So we want to know when, I guess, k is equal to 4. The next one, k is equal to 5. So that's C7. 5 plus 2 is 7. And then we have 5 minus 2 is, this is going to be 3. 5 plus 2 is 7. And this is 6. And then this is k is equal to 5, so C sub 5. What does C sub 5 equal to? C sub 5 is equal to this, a negative. So let's change that C sub 5 to a negative. So 7 times 6 times 5 times 4 times 3 times 2, so that's going to be another factorial. We have a negative 3 on top. So that's a negative 3. So that's a 3. That's kind of new to us. And then we have 7 factorial on the bottom. And then C sub 1. So we're seeing this in terms of C sub 1. You can probably guess that k is equal to 6. Is going to give us a 0. So when k is equal to 6, we have 8, C sub 8. But the important part here is that this is equal to 6, and C sub 6 was equal to 0 already. So let's just say this is equal to 0, and we don't need to go any farther than that. So we can see that the even C's are going to be equal to 0. And then let's do one more. K is equal to, our last one was 6, so let's do k is equal to 7. So this is our relationship. And when k is equal to 7, we have 7 plus 2, that's 9. 7 minus 2 is 5. And this is 7. 7 plus 2 is 9. 7 plus 1 is 8. And we have this expression, but C sub 7 is equal to minus 3 divided by 7 factorial times C sub 1. And so what's that equal to? In the numerator, we have a 3 times 5 negative 3 times 5 and then in the denominator we have 9 times 8 times 7 factorial, so that's just 9 factorial, and then C sub 1. Alright, so it looks like there's going to be a pattern here. So just take a couple of guesses. We have C sub 9. We can tell what C sub 10 is. C sub 10 equals 0. And just by looking at this, C sub 11 should equal to, it's going to be a negative. And then is going to be a negative 3 times 5 times 7. Looks like we're going to be multiplying the even numbers. And then this is going to match the subscript 11 times C sub 1. Okay? So, that's our C's. Now let's see if we can put it all together as our... let's see if we can put it together in our series. Now remember, our series should equal to this. What's that equal to? That's equal to C sub 0 plus C sub 1 times x plus C sub 2 times x squared plus C sub 3 times x cubed plus C sub 4 times x to the 4th when we get the picture. So what do we have? We have C sub 0. Well, that's just C sub 0 by itself. So this should equal to let's see, equals C sub 0 plus C sub 1 times x plus, now let's start with C sub 2. C sub 2 is equal to negative C sub 0. So that's a negative C sub 0 times x squared. That's C sub 2, right? C sub 3, maybe I should have just copied this. C sub 3, what was C sub 3 equal to? C sub 3 was equal to this thing. that has a factor of c sub 1. C sub 4, remember that? That was equal to 0. So from here on, all the even powers will be 0. What's c sub 5 equal to? C sub 5 was equal to this. Remember, we didn't simplify it, but this looks like it's just going to be 3 factorial. C sub 5 is equal to this. It's negative again. C sub 6 was equal to 0, if you remember. Plus c sub 7, x to the 7th, where c sub 7 is equal to this thing. Oops, there's plus etc. Okay. So if I take a look at my even powers, I can combine them into one, and then they all have factors of c sub 0. Well, there's only 2 of them, but you know, if I had more, ideally these things would have c sub 0s in it. But in this case, I only have 1. So let's put an equal sign here. C sub 1 or c sub 0 times 1 minus x squared. So we see that these two terms here, c sub 0 and negative c sub 0 x squared, will give me this, plus c sub 1 times, now I have a lot of c sub 1s. My first one is has an x. My next one has a negative 1/3 times x cubed. So I have a minus 1, not 1/3, sorry, 1 over 3 factorial times x to the 3rd power. Plus, actually it's a minus, so minus this thing, minus 1 over 5 factorial times x to the 5th power. And then my next term, minus 3 over 7 factorial x to the 7th minus, and if I were to keep going, the next term is the 9th term, so minus 3 times 5 divided by 9 factorial times x to the 9th minus, if we go one more, 3 times 5 times 7 divided by 11 factorial x to the 11th power. And then there's a pattern that goes on. So what do we have here? We have one function that can be written as this series, and the series stops at x squared, so it's just going to be 1 minus x squared function. And then we have another function that's this series, that's x minus 1/3, 1 over 3 factorial x cubed minus 1 over 5 factorial x to the 5th, etc. And that's being multiplied by arbitrary constants. So we got, in our example here, we got our arbitrary constants built in. So usually we'd have a C1 and C2, but now we have a C0 and C1. These are our arbitrary constants, and then these are our functions that are linearly independent from each other, and they would satisfy the differential equations. So if you can write this into a series, go ahead and give it a try. But otherwise, we can just write it extended like this, and we can imagine that we can find a pattern if we needed to. All right. So that's our first example of the series. Here's our second example. This is an actual initial value problem. So we want to solve the initial value problem. We have a differential equation, x squared plus 1 multiplied by y double prime plus 2x multiplied by y prime is equal to 0. And then we have initial conditions at 0. Y is going to be 0, and then the derivative is going to be equal to 1. All right, so we're going to assume that if we divide this out, let's see, just from the theoretical aspect of our power series solutions around points, if we divide this out, oops, I just want this. This is our p. Q is going to be equal to 0, but this is our p function, and this is going to be defined for everything. So this is going to be an analytic function around 0. We definitely want to be around 0, and this is defined analytic at 0, so we don't need to worry about any issues there. So we can just go ahead and take our differential equation and find the power series solutions for that. So just like before, when we set up our power series solution, we're going to assume that our power series is y is equal to this c sub n x to the n, and goes from 0 to infinity. And so we want the second derivative. So our first derivative and second derivatives are given here, and they're generally always going to be like that. And so we're going to want to take this and replace our derivatives, our second derivatives and our first derivatives, by whatever we find. We don't get to put in our y, but our y double prime and our y prime goes back into our differential equation. So let's see. We need to distribute this series. So we have the series that needs to get distributed to the x squared and to the 1. And so how's that going to look like? I believe it's going to look like this after we distribute. So we distribute, and then we have this term with an x, and then this term with a 1, and then we haven't touched this term yet. So now let's put the x squared in, let's put the 2x into that last series, and this is what we're going to get. So the x squared goes into the series, and then this becomes x to the n. This didn't change, and the 2x goes into the series as 2 times x to the n minus 1. That gives us x to the n. Okay, so now if we scan through the series, we see that the middle one has an x to the n minus 2. So I definitely want to change that. So I'm going to do the shift to a k again. For the middle term only, I'll replace n with a k plus 2. So that would just give me a k here. And then I'll replace the others with k's, just so I can have the same index for all of them. So nothing really changes here except my index went from an n to a k. Same with the last series. So the middle series is the one that changes. In for n, I'm going to put k plus 2. In for n, k plus 2. So k plus 2 minus 1 is going to be k plus 1. In for n, I put k plus 2. And then in for n, I put k plus 2. So k plus 2 minus 2 is just going to be k. And as I'm doing that within the series, my index has to drop by 2. So I add 2 inside, I subtract 2 for the index. And this is my new series. Alright, so now all my series have an x to the k power, which is what I want. And the next thing I want is to match the indices. So I take a look at the largest index, that's 2. So this is going to stay the same. I need to start this at 2, so I need to put 2 terms outside when k is equal to 0 and k is equal to 1. And likewise here, it starts at 1. I want to start at 2, so I'm going to put k equals to 1 term outside. So what am I going to get? I will get this term. So this stays the same. Our first series stays the same. Our second series, now our second series has 2 terms taken out. When k is equal to 0, I'm going to have 2 plus 1 plus 2 times 1 times c sub 0 plus 2, so that's c sub 2, and then x to the 0 power. So that's the 0th term. And then I have one more term to pull out, and that's the first term when k is equal to 1. Put k is equal to 1 in here, and then you would get this term. So the 0th term and the first term are gone from this series, so now my series starts at 2. And notice everything else is the same, except I took 2 of them out. So similarly here, I want to start at 2. So I'm going to take out the k is equal to 1 term, and so when k is equal to 1, I get this term. And then now my series is going to start at 2 instead of starting at 1. So now my series starts at 2. Let's just do some simplifying. So the first thing I can think about doing is putting all these terms that are not part of the series together. So there's these 2 terms, and then there's this 1 term over here. I can put all that, simplify it a little bit. X to the 0 is equal to 1. And then I have a couple of x to the first terms. So x to the first is just x. And then a couple of these terms just got grouped together here. So now I have my constant term and my linear term, and then now my series starts at the quadratic term when k is equal to 2. I want to put that together. So how are we going to put that together? So they have the same starting point, they have the same index here, so I can take my first term, k times k minus 1 times c sub k, and then I'll take my second term, and then I'll take my last term, and those terms can be, they all have an x to the k that I factored out, and so now we just have this. The other thing to possibly do is to put all the c sub k's and c sub k plus 1 and k plus 2, etc. together. And so we can do that in a couple of steps. So in our next step over here, let's take the c sub k plus 2, and I have a k times k minus 1 c sub k, and then there's a 2k, so I'll put that together into one parentheses and then factor out a c sub k. And then probably something minor, but we can also simplify this thing in here. we have a k, k minus 1, and then k minus, or 2k, and so we can just simplify that. Now, we have to take a look at each of these terms to equal to 0, because after all, this thing is supposed to be equal to 0. So the linear term, or the constant term, is 0. The linear term is 0, and all these other terms, starting from the quadratic on, should equal to 0. So what do we have here? Well, we have some relationships between the c's. This, first of all, is going to be equal to 0, so that's going to give us a c2 equal to 0. So already c2 is gone. We have this term over here equal to 0. So if we set that equal to 0 and we solve for the c sub the largest c value, and so c sub 3 is equal to 1/3 c sub 1. Now for the rest of them, and that's k that's bigger than or equal to 2, we want this whole thing to equal to 0. So this whole thing is equal to 0. And if you solve for c sub k here, you'll bring this over to the other side and you divide out, and you're going to get negative k over k plus 2 c sub k. So it looks like we can find relationships for c sub k. So I did a few of them in a row here. When k is equal to 2, then c sub 4 is equal to this times c sub 2, but c sub 2 is equal to 0, so that's done. When k is equal to 3, I have c sub 5 equals to negative 3/5 c sub 3. What's c sub 3 equal to? C sub 3 is equal to this, so that gets combined. When k is equal to 4, I have c sub 6. Remember, I'm looking at this relationship over here. I have c sub 6 is equal to 4 over 6 c sub 4, but c sub 4 was equal to something c sub 2, which is equal to 0, so this whole thing is equal to 0. Alright, so when k is equal to 5, I have so k is equal to 5, this is c sub 7, and then this is going to be 5 divided by 7 with a negative c sub 5, and then that's equal to c sub 5 was equal to 1/5 c sub 1, and so that gives me a negative 1 over 7 c sub 1. So then that's what we have. So I think we can write this in general. Generally, if we have an odd number that can be represented as c sub k plus 1, let's use n here, then this is going to be an alternating sequence, and then it's going to be always a 1 in the numerator, and then 2n plus 1, and then c sub 1 in the denominator. Alright, so let's see, what is our series actually going to look like? So our solution, let's see if we can put our solution down. So our solution is equal to this. Let's call it solution. That's equal to this, which is equal to, again, c sub 0 plus c sub 1 times x plus c sub 2 times x squared plus c sub 3 times x to the third, etc. So what do we have? C sub 0, we didn't really find a value for C sub 0 if you remember, so C sub 0 is just that arbitrary constant that we should expect. C sub 0 plus, what was C sub 1? Did we find a value for C sub 1? We didn't find a value for C sub 1 either, so just say C sub 1. C sub 1. C sub 1 times x. Alright, what's C sub 2? C sub 2 turned out to be 0. So here we have another 0 times x squared. What's C sub 3 equal to? Do we get a value for C sub 3? C sub 3 is negative 1 over 3 C sub 1. So negative 1 over 3 C sub 1 x to the third power plus C sub 4 is equal to 0 plus C sub 5. So what's C sub 5 equal to? C sub 5 is up here. It's 1/5 C sub 1 plus C sub 6. Oh, C sub 6 is equal to 0. X to the 6 plus C sub 7 So what's C sub 7? C sub 7 is equal to this. And we found a pattern for this already, but we'll take advantage of that pattern later. So C sub 1 looks like it's just, or C sub 0 looks like it's by itself. So y looks like y sub 1 is going to equal to C sub 0. And then for the others, the ones without the zeros, we can just imagine taking out the C sub 1 because they're a constant. So y sub 2, our second linearly independent function, is going to be equal to essentially the rest of these things. Okay, so let me just copy this down and take away the odd or the even terms, because we're not counting the even terms here. So it's basically this, and we want to factor out a C sub 1. And then it looks like it's that alternating term that's going to be multiplied by x to the whatever the power is. So if we want to write this as a series with alternating terms, this is going to be x raised to the 2n plus 1. So this is your second series. Now imagine all this being multiplied by the arbitrary constant C sub 1, and then this is essentially what we get. So these are our two series. By the way, if you can ever write your series like this, any of your solutions, you can generally write the summation. So your y sub 2, if you want to rewrite it, y sub 2 is actually equal to the series where these are your constant terms. But it looks like we're only dealing with the 2n plus 1, the odd terms. So this is another way to rewrite your y2. So these are our two linearly independent functions, y sub 1, which is equal to just 1, and y sub 2, which is equal to this series. Okay? Alright, hope that helps. Now that we have the general solution, we want to use the initial conditions to solve for C1 and C2. So if we take a look back here, the linear combination of these things with C1 and C2 is going to be our solution. So it's really just, let's rewrite our general solution a little bit differently. C sub 0, or y is equal to a constant, C sub 0, plus C sub 1 times the rest of these things. So C sub 1 times the rest of these things. So you can imagine that each of these things are being multiplied by C sub 1. Let's actually do that, because when we play around with our initial values, initial conditions, then that might be helpful to see. So each of these things, let's take out the parentheses. So C sub 1 times x, and then this thing times C sub 1, and this thing times C sub 1, etc. So this is what we have. Now when we put 0 in there, y of 0, then we're actually, in this original function, we put 0. Each of these terms after the first one have zeros, have an x in there that we're going to put 0 in, so that's just going to disappear. So y of 0, y of 0 is actually just C sub 0, and C sub 0 is equal to 0, because y of 0 is equal to 0, so this whole thing is equal to 0. So our solution must have C sub 0 is equal to 0. Now let's find a derivative. So to find a derivative, let's think about taking the derivative of this. So y prime. Derivative of a constant is 0, so that's going to disappear. The derivative of this term is just going to be C sub 1. The derivative of this term is going to be something with an x squared. Now I want to pause for a moment and notice that the rest of these derivatives will have an x term in it. So this is 7 and 6, etc. So I don't want to try to mess around with this. I mean, I think we can figure this out. That's just going to be this thing. But the point is that each of these terms from here on out will have x's in it. And the reason why that's important is because what you're trying to do is you're trying to figure out what y prime of 0 is. So what you're going to do is you're going to put 0 in for x, and that's going to lead everything else here to disappear, and then all you would have left is C sub 1. And according to your initial conditions, C sub 1 is equal to 1. Because y prime of 0 is equal to 1, and these two things are going to be equal to each other. So essentially, your general solution that has y1 and y2, so let me see if we can write that out. Your solution then would be y equals y1 times C sub 0, which we know it's going to be 0 because that stuff's going to disappear, plus C sub 1 times y2. So we know that this is going to be 0. So this is going to be 0, and then plus C sub 1. C sub 1 is equal to 1, So that's just going to be 1 times y sub 2, and y sub 2 is just this series. So this is going to be your solution. So y equals this. Okay? So if you look at it carefully and somehow derive Taylor's polynomials, you'll see that this is actually the arctan of x. Okay, we don't need to worry about that. The fact that we found a series solution is good enough. If you can identify this as a function, that would be great, but in general you won't be able to, so our solution here is fine. Okay, I hope that helps.